Okay, guys, welcome to class. I'm not here today, as you can see, and you have a sub, and we needed to finish the notes. So I am finishing the notes with you right now. Unfortunately, I have some bad news for you. Voice mod is not working, so I can't do it in baby voice. But you can hear my normal voice, and I'll finish this up. Now, period one, we haven't done this problem yet. Period two and three, you guys have already done most of this problem. So you could probably fast forward a little bit, get to where you guys were. So this problem, we're going to take what we learned in our notes last class, which is that when you're combining random variables, right, you can add the expected values if you add them. You subtract the two random variables, you subtract the expected values, and then to combine the standard deviations, you actually add the variances. Remember, it's called the Pythagorean theorem of statistics. You add the variances together, and that works, and then you square root to go back to standard deviation. So it doesn't matter if you're subtracting the two random variables or you're adding the two random variables, always add the variances. So let's go to this problem and let's go through different transformations and let's get these. So first one wants to take the y random variable and times it by 0.8. So your mean is going to be 0.8 times your old mean, which was 100 for the y variable. So that's going to be, I think that's like 240 if I'm not mistaken, 240 for the new mean, 0.8 times y. Now the standard deviation is going to also be 0.8 times the standard deviation of the y group, which is 16. 0.8 times 16 is going to be 12.8 for your standard deviation. So there is the answer to the A part. The B part, pretty straightforward too. You're going to take the x variable, you're going to multiply it by 2, you're going to subtract 100. What's that going to do to the mean? And what's that going to do to the standard deviation? So for the mean, you're going to take your mean of your x, you're going to multiply it by 2, and then you're going to subtract 100. So you're going to end up getting 140 for your mean after the transformation. And then for the standard deviation, you're going to take your 2, you're going to multiply by the standard deviation. You are not going to subtract 100. So the standard deviation after the transformation is actually 20. Be careful on that one. Do not subtract 100. For part C, they want you to do the x random variable plus 2 times the y random variable. So to do this transformation, you're going to combine the two random variables. So for the mean, no big deal. Take the mean of the x group, going to add it, 2 times the mean of the y group, and you're going to get 600 there plus 120. So you're going to end up getting 720 for the mean when you combine those two ranges. Now, for the standard deviation, here's the tricky part. You're going to do, you cannot add the standard deviation. So the common wrong answer, don't write this down, is to do, someone's going to do 12 plus, and they're going to do 2 times 16. And they're going to give that as their answer. That is not how we do this. We cannot add the standard deviation. So what we need to do is take 12 squared, which is the variance of the x group. We need to add it to the variance of the y group. But the y group has been doubled. So instead of being 16 for the y group, the standard deviation was actually 32. So you're going to take your 32 and you're going to square that. And then, get the fly out of here. And then you're going to square root that after you combine it. So this variance of the x group, the variance of 2 times the y group, you're going to square those, add them together. You get 1168 square root, and you end up getting 34.18 around there. I rounded it up a little bit. 34.18. So there is part C of combining those two groups together. Okay, part D, do over here. Let me go a little higher. On the D group, we're going to do 3 times the x random variables minus the y random variables. So for the mean, pretty straightforward. Take your 3 times your mean of your x variable, and then subtract your mean of your y variable. Pretty straightforward, exactly what it says. So you got 3 times 120, that's your 360, 360 minus 300. You end up with a mean of 60 on that one. And then your standard deviation, though, a little bit more complicated. You're going to do 3 times the standard deviation of your x, which is 12. So that's 3 times 12. That's going to be 36. You need to square it, so you've got the variance of the x group. You need to add it to the variance of the y group, which is 16 squared, and then you're going to square root that. Remember, do not subtract. I know they are doing subtraction, but you always add variances. So you get 1552, you square root it, you get 39 point about 4. I mean, it's pretty close to 39.4. There is your standard deviation of that group. And then the last one, which we did not get to do in periods 2 and 3, so everyone's going to be watching this one. We're adding 2 y variables. So y1 plus y2, it's like you played the game twice, and you're adding the distributions of both times you played the game. You can only do this stuff when you're combining, when you have independence between the two things you're combining. So if your two things are independent, you can combine them. So how's the mean going to look? Well, the mean is going to be fairly simple on this one. You're going to take the mean of y when you did it the first time plus the mean of the y's when you did it the second time. So you're going to end up getting a mean of 600. Someone's going to say, why don't you just double it? Well, that works on the means. That doesn't work on standard deviations, so I usually don't write it like that. So on standard deviations, we're not doubling the standard deviation of the y. We're taking the standard deviation of the y plus the other standard deviation y group, but we can't add standard deviation. You're going to add the variance the first time you did it, plus the variance of the second time you did it for the y group. And then you're going to square root that. So 16 squared plus 16 squared, and then square root that. You should get 22.6, right around 22.6. So there's your standard deviation. So don't do 16 plus 16. 32 is going to be a really common wrong answer. Somebody's going to do 32. Someone's going to double 16 to get, oh, it's 32 that way. So be super careful. Add the variances together. Okay, so we're done with that problem. Hopefully that didn't go too bad. Now we want to do the same stuff with a word problem. So here's your chance to do it on your own. So if the sub can pause the video right now, you guys can make an attempt, try and do A and B, and then play the video and you can see what the answers are. Okay, so you guys are back. You just finished the problem. Hopefully you talked to your partners and you figured out what you did, but let's see how we do it. Delivery companies' trucks occasionally get parking tickets. Based on past experience, the company plans that the trucks will average 1.3 tickets. So the expected number of tickets is going to be 1.3 a month with a standard deviation of 0.7 tickets. Okay. If they have 18 trucks, what are the mean and standard deviation of the total number of parking tickets? They have 18 trucks. So it's like truck 1 plus truck 2 plus truck 3 plus truck 4. It's not 18 times the trucks. Okay, I know that will work for mean, but it won't work for standard deviation. So you got to imagine you're taking these 18 trucks and you're adding them together. So sort of like the last part of that last example. So the mean, pretty straightforward. The mean is just going to be 18 of those added up. So you got like 1.3 plus 1.3 plus 1.3 plus blah, 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 right? 18 times. So that one could work. You could do 18 times 1.3 on that one, and it will still give you the same answer. You're like, cool, I can totally do that. So we get 23.4 tickets is going to be the average of all the 18 trucks, but the standard deviation will be different. It's going to be not 18 times 0.7. It's going to be 0.7 squared for the first truck, plus 0.7 squared for the second truck, plus 0.7 squared for the third truck, plus 0.7 squared for the fourth truck, blah, 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 all the way till you get to 18 of them. And then you will square root it. A little bit bigger than the Pythagorean theorem because you got 18 trucks in this one. So 0.7 squared is 0.49. You could just take the 0.7 squared and you could just times that by 18 because you're basically adding up 18 of the variances. So you could do the variance times 18. There's 18 variances, and then you're going to square root that after you've added up all those 0.49s. So 2.97 is our standard deviation. 2.97 tickets. So the middle of all the 18 trucks is going to be about 23 tickets for your whole fleet, but the standard deviation of your whole fleet is about 3 tickets basically. So, some months you may hit 26, some months you may hit 20. It gives you some idea of how much this is going to cost you if you own this company. What assumption did we make when answering this? The assumption that you guys made is that the trucks are independent of each other. The trucks are independent of each other, right? When one truck gets a ticket, I did not spell that right. Independent of each other. So when a truck gets a ticket, right, it doesn't affect whether one of the other trucks get a ticket. You have 18 different drivers. They don't affect each other when they get tickets. That's kind of thing we're hoping that we have independence like that. So there we go. You see how it works when you have multiple trucks of the same distribution, basically, that you're adding them up. Okay, next example. This one is very similar to homework. There is a problem on homework that looks like this. So I love swimming problems, right? I used to coach swimming for I don't even know how many years I've coached swimming, but it's been at least, I haven't coached in a few years, but overall I probably have coached a total of 11 or 12 years of swimming. So let's see. So we're looking at a relay race. This is the medley relay. So that means one person's going to swim each stroke. What are the mean and standard deviation for the relay's total time? So we're trying to find. So if you want to try and do this on your own, stop the video now, pause, go for it. Do the video, do it. Okay, welcome back. Unpause. Let's see how it went. What are the mean and standard deviation? Okay, mean's pretty easy, right? We're going to do one of each other. You're going to swim backstroke, and then your next one's going to swim breaststroke, and the next one's going to swim butterfly, and the next one's going to swim freestyle. So that's all we're doing. So the mean, you add up all of their times, right? You got your 50.72, you got your 55.51, you got your mean of that group, 49.43, and you get your mean of the freestyler. And you add those all up, and that should be their time. Plus 49.43 plus 44.91. And you end up getting 200 seconds, 0.57. And this must be in seconds. So there's the middle. The standard deviation, though, this is going to be a little harder to calculate. So standard deviation, right? 0.24 squared variance plus 0.22 squared variance plus the variance of the butterflyer plus the variance of the freestyler. Oops, I put one there. Square. Add up all the variances and then square root. 0.24 squared plus 0.22 squared plus 0.25 squared plus 0.21 squared. And you end up getting 0.461 after you square root. It's about 0.461 seconds. So the standard deviation is about a half of a second, right? Their time should be right around 200 seconds, but we understand with variation of the swimmers, we're going to get about a half of a second of standard deviation. Okay. This problem has an extra wrinkle to it, and this is what they like to do in these type of problems. It would be too easy to just make you get the center and the standard deviation. So they add in this normal distribution part. I'm interested to see if any of you got the normal distribution part all on your own, because it's not the easiest thing, and it's been a while since we've done normal distributions. So what they told you up in the problem is that the swimmer's time follow a normal model. So that means that this overall time, when we add all these normal models together of these 4 different swimmers, we are going to get an overall model that is also normal. So our normal model, we know, has a mean of 200.57, right? Pretending that the normal model for the total time of all these swimmers, we know the middle, right, is 200.5 seconds. And the standard deviation we already calculated was 0.461 seconds, right? So we know the middle is 200, and we know the standard deviation is 0.461. So with that information, we should be able to calculate some probability. So the team's best time so far this season was 3:19, which was 199.48. Do you think the team is likely to swim faster than that? So 199.48 is somewhere over here on this side. I don't know exactly how far. I haven't done the z-score to see. So 199.48. We would like to find the likelihood that our team will get a time faster than this. There's a couple different ways you can prove it. You can do a normal calculation and find the area. You can do the z-score and just tell me, oh, that's pretty far away. Let's do the z-score. So take the z-score, which would be 199.48 minus your mean, 200.57, divided by standard deviation, 0.461. Let's see what we get. 199.48 minus 200.57 divided by 0.461. I get a z-score of negative 2.36. That's pretty significant. So you could right now say, you know what? I think that's pretty far from the mean. That's almost 2.5 standard deviations lower than the mean. You know that doesn't happen very often. You might say, no, I don't think it's going to happen. If anyone wants to do a normal model justification using your probabilities, you could also pulled out your calculator and did your normal CDF if you wanted to. So I'll do this one in red, but you could totally have done it. The lower boundary, remember, is 0 or negative infinity. It doesn't really matter on this one. The upper boundary was that 199.48. Your mean was your 200.57, and your standard deviation was your 0.461. So you can do it with the calculator. So if we do our calculator, remember second distribution, normal CDF, we're going to go from negative infinity. Hey, it's already there. 199.48, and then your mean was 200.57, and your standard deviation was 0.461. Let's see what we get. 0.0090. 0.0090. That is not very likely to happen. So you could justify it with that. You could justify your answer with this, but you would write a sentence and you would explain to me, hey, I don't think it's going to happen because look at how unusual that 199 is from our model of combining all those times. So that, I don't know about you, but that's a fun problem. I enjoy that problem. Swimming problem is sort of cool. The last problem, you guys, I don't think have this one on your handout. Don't think you do. I think you had that one. You definitely had the ticket ones. I don't think you had this one because I was trying to save some paper. But there is one like this, I think, on your homework. And I just wanted to show you one part, and that was the part C, really, on this one. So if you want to take a break, you can. You can pause it right now. You guys you can't try this one because you don't have it. So don't pause the video right now and just watch, okay? Don't copy it down totally. You can copy down the work, but I need you to understand this for one of your homework problems. So let me see. Get that out of the way. Okay. So we got how much more cereal do you expect to be in the large bowl? So they give you two size bowls. You got a small bowl for cereal, you got a large bowl for cereal, and they have different means and different standard deviations. So they want you, how much more cereal do you expect in the larger bowl? Well, basically, that's the expected value. So the larger bowl is 2.5, so that's my Y one. Should have called it L, I guess. And then my expected value for my smaller bowl is my X1. I should have called that S. So 2.5 minus 1.5. We expect there to be 1 ounce more in the large bowl than the small bowl. What's the standard deviation of this difference? Okay, standard deviation of subtracting the two bowls. So we're doing y minus x. So the standard deviation will be the square root of the standard deviation of the y group, but not the standard deviation, the variance of the y group, plus the variance of the x group. Remember, it's got to be variance. So 0.4 squared plus 0.3 squared. So that ends up 0.25 and then square root it. So you end up, wow, why did I not know that? Square root that and you end up getting 0.5 because it's like a 3, 4, 5 right triangle. They're getting tricky on us like that. So 0.5 is your standard deviation of the combined subtracting of the two bowls. Ounces, right? Okay, part C, this is the one I really wanted to show you. We don't really need to do D and E. So if the difference follows a normal model, key right here, normal model, what's the probability the small bowl contains more cereal than the large bowl? Well, we've already subtracted the two bowls, and they just told you that you have a normal model. So if you subtracted the two bowls and they told you have a normal model, the middle is 1 ounce because we did large minus small. Standard deviation we know is 0.5. Okay, they asked you what's the probability the small bowl contains more than the large bowl? You got to think, where would that be on your normal diagram? Small bowl contains more than the large bowl. Small bowl, that would mean the S number would be bigger, the L number would be the smaller one. So that means when you do the subtraction, if S is the bigger number, you're getting negative numbers. So basically, they're asking you to figure out the probability that you're a negative number. Because whenever you get a negative number, that meant the small bowl had more cereal than the large bowl. So your boundary is at 0, and you're to the left on that one. So to calculate that probability, we're going to use our calculator, right? We're going to use normal CDF. Don't forget you're supposed to label. So the lower boundary is going to be negative infinity. Your upper boundary is going to be 0. Your mean is going to be 1. Standard deviation is going to be 0.5. This is actually exactly 2 standard deviations. So it should be really close to like 2.5%. But let's see. Let's get the exact answer. Normal CDF. Our upper boundary is 0 on this one. 1 ounce is the mean. 0.5 is standard deviation. We get 0.022, very close, right, to 2.5%. 0.0228. If you did this on your Z table, you would get about 2.5%. It'd be really close, right? If you did with, so why did they give you one that was exactly on 2 standard deviations? I don't know. Maybe they were being nice to you. But that's how you do it. If they ask you can you figure out when one is greater than the other? Then when they ask you if one is greater than the other, you're going to have to subtract, and 0 will be your boundary, and you're either going to be positive or negative depending on the way that you subtract it. Because think, someone else could do small bowl minus large bowl, and if you subtract it that way, okay, you would have been positive numbers. So 0 will still be your boundary, but it'd be your lower boundary, and you would have done positive numbers. So, so that is it for the notes. That's what we needed to finish today. So you got a 25 minutes. Hopefully you guys done. That was about 30 minutes probably stopping and stuff. So the rest of class, I assigned 2 things on AP Classroom. You guys go with your partner, work on AP Classroom, do those. Don't do it like last time where I assigned them and like 3 people did them. Don't make me mad, okay? Because I will check. I will log in and I will check and see who did it and who didn't do it. And I do not want you to make me mad. I want you to make me happy. And I log in and I see that like everyone did it that was there that day. So do the AP Classroom, talk to your partner, figure that out. If you finish that up and you still have time in class, which I'd be shocked, then go ahead and work on the homework. Okay, the rest of the class. Totally, totally fine. But that is it, guys. Have a good holiday. Sorry I couldn't be here this last day. I had an engagement I had to go to. So have a good holiday season. We will see you in 2 weeks. Make sure you work on your homework. It's going to be due the day you get back on January 3rd. And also, don't forget to sign up for your dual credit. Let's get that done. Okay, guys, have a good break. We will see you later.